Hello, everybody. For lesson 6.10, I want to walk you through the development of the projection formula. I feel like the lesson did a pretty good job of it, but seeing it done is always useful as well. I think I'll leave the development of the area and the volume formulas up to you to go through on your own. They are formulas that you should be able to develop, and that way you can avoid having to memorize them. But we will have other memory aids in the future. So, projections. The idea of a projection is kind of like one of a shadow. Let's set something up here. We'll make it maybe an acute angle to make things a little bit easier. So here's the vector A, here's the vector B. The vector projection of A onto B, you drop a perpendicular down, an altitude down, like that. And the projection of A onto B is like A's effect on B. How much of A is going in the B direction? If B were one of our unit vectors like I hat or J hat, then basically this vector projection would be that corresponding component of this vector. You can think of the projection of A onto B as being the B component of A, but that's a little bit confusing because I don't think I would use B as a basis for anything. Okay. The projection of B onto A actually looks like it might actually be even the vector A, and that's possible in this case. The projection of a vector onto another vector may be the other vector. Let's just focus on this vector right here, which is the projection of A onto, A onto B. So we start with a scalar triangle. Let me just draw a different triangle here. Okay. Here's the angle between the vectors. It's the tail-to-tail angle, theta, right there. This length is going to be mag A. And I am set to create a ratio. This is the magnitude of that projection of A onto B. Now, some texts will really assign a lot of importance to this right here. They call it the scalar projection of A onto B. I'm not that worried about it. We can find some uses just for this number right here. But I really don't think you need to memorize anything. We're looking here at a right angle triangle situation. We're using some grade 10 trig. I see that the cosine of theta is going to be equal to the magnitude of this projection, A onto B, divided by the magnitude of A. And let's just talk about one thing that didn't come up a lot in the lesson, the reason why we need these absolute value bars sometimes around this cosine of theta. I'm kind of assuming that theta is acute. If theta were obtuse, then the cosine of theta would be a negative number, and I don't want this distance to be considered negative. So that's why you'll often see the absolute value bars show up here. It is a different symbol. Here's another interesting little tidbit. Cosine of theta is a scalar quantity. So these bars, that's not the magnitude of the cosine of theta. That doesn't make any sense. It's the absolute value of the cosine of theta. But inside those bars, that's a vector quantity. So this is not the absolute value of the vector A. That doesn't make any sense. It's the magnitude of A. Those symbols look an awful lot alike, but they should be read differently. Okay. So this means that the magnitude of this vector, the projection of A on B, you'll get tired of writing that real soon if you're not already, is given by the magnitude of A multiplied by the absolute value of the cosine of theta. Now that's fine, I suppose, but if I want to do a projection of two three-dimensional vectors, then I would need to know the angle in between the vectors. To find that angle in between the vectors, I would probably use the dot product. Well, how about instead of doing that, I recognize that this is really close to the dot product. So what I'm going to do is I'm going to make it the dot product by multiplying by, the only thing I'm allowed to multiply by is 1. So I'm going to multiply by the magnitude of B over the magnitude of B. And that way I get, for the scalar projection, or the magnitude of the vector projection of A on B, I get mag A These are just scalars, and scalar multiplication is commutative, so it doesn't matter what order you perform them in. Mag A, mag B, absolute value of the cosine of theta, which is not exactly the dot product. Oops, sorry, I have multiplied by 1, so there is a mag B in the denominator. It's not exactly the dot product, but it is the absolute value of the dot product. So let's say this is the absolute value of the dot product. And we'll be playing a game later called, we're actually always playing a game called scalar vector neither either. A is vector, B is vector, A dot B is scalar. So those bars are not magnitude bars, they're absolute value bars. Okay. Okay, now to make this into a vector, to get back to here, what we want to do is use this as the magnitude of a unit vector in the direction of the projection. Now, let's go ahead and assume that this projection is of magnitude greater than 1. So here is b hat. Sorry, it took me a while to figure out what vector I'm in the same direction as. Okay. We don't need the projection to be longer than the unit vector. If our magnitude is less than 1, then we're just stretching by a factor that is less than 1, and the vector will compress, I suppose. Okay. So to make this into a vector, sorry for the order here, let's just go over here. The vector projection of A onto B is going to be a scalar multiple of the absolute value of the dot product of A and B divided by the magnitude of B multiplied by B hat. And I could stop here, but this is kind of awkward. I don't want to have to look at the vector B and find its magnitude. Let's substitute in what we know for B hat. B hat is a vertical stretch of the vector B. It's the vector B multiplied by the reciprocal of its magnitude. Okay. I'm out of space on this page, so I'm just going to squeeze this down here. This gives me absolute value of A dot B divided by, now I see mag B times mag B. And up here I saw mag A cosine theta and recognize that as the dot product of two different vectors. When I see mag B times mag B, and I include perhaps the angle in between B and B, well, the angle in between B and B is going to be 0. And the cosine of 0 degrees is going to be 1. So again, I'm multiplying by 1 here, but not in a format of a fraction where the numerator and denominator are the same. I'm going to multiply by 1 by multiplying by the cosine of the angle in between those vectors. And by doing that, I can replace mag b times mag b, or mag b squared, because again, maybe I don't want to even have to calculate the magnitude of b. And I can replace it with what turns out to be a simpler operation. And I get the formula. Absolute value of A dot B divided by B dot B multiplied by B. Okay, whoops, I lost something along the way here. Oh, yes, right here. In the case that A is obtuse to B, then I would want to make sure that this scalar multiple was negative if needed. So that on that step is when I should have removed those absolute value bars. Sorry about that. Okay. Now for the punchline, and this is a formula that you should be able to develop. You should be able to sketch. You should be able to understand and discuss your way through. But in the middle of a question, say on areas or volumes, you also probably want to know it. And as far as memory aids go, it's not that bad if you look at it. The projection of A on B is A dot B divided by B dot B times B. If you understand what the projection is going to be, you understand that the projection of A on B has more in common with B than it has with A, and that's why there's more B's. There's a bit of A-ness to it in that it only goes as far as A goes in the B direction, and that's where that A comes in. Make sure you get these order right. The projection of B on A would be B dot A divided by A dot A times A. It doesn't matter what order you have in the dot product because A dot B is equal to B dot A. But you will want to have the correct vector dot product down here, and it needs to be a vector that is in the same direction as or opposite to B, which means it needs to be collinear to B, which means it needs to be a scalar multiple of B. So make sure that you have the correct vector out there. Okay, try it out. Try out the area questions and the volume questions as well, and let me know if you have any concerns.